I know, because I'm going, right up. No, I got my okay, I changed the word. Okay, I didn't do it. It needs schematic, so I guess you can do it on a different pattern. Yeah. How do my soft partnership? Yeah, I don't know. That's what's true. Okay, so I'm just so glad the rest are technically different.
Okay, let's see. Sarah B, Claire, Matt, Luke, Jaden, Emma, Liza, Stuart, Ethan, Anya, let's see, Olivia, yep, Kushal, Diego, Darwin, Sean, Jules, right, okay. Doa, Matthew, Colin's here. Emily, Sarah B, right? Let's see, Emily, no. Okay. Rennick, yep. Sarah T, McKenna. I think I got everybody here. Okay. Okay. All right. Okay, so about time to get started. Last time we were talking about polar coordinates. We're going to keep talking about polar coordinates today, and then hopefully make it through cylindrical coordinates and spherical coordinates. And I'm hoping maybe a little further than that, but I'm historically optimistic about what we can get done in a day. Anyway, let's dive in. So we were talking about this region here, the unit disk, and how does one find polar bounds for this? And just as a first-time example, the way that you go all the way around is to just say theta goes from 0 to 2 pi, because that takes you all the way around. Right now, we'll make sure that you don't, fall for the mistaken belief, well, you're starting and ending in the same direction, so shouldn't it be 0 to 0, right? You need to actually make it all the way around. Further, make sure you don't go twice around, because then you're double counting. And in particular, do keep in mind, we're doing a change of variables, right? And for the change of variables to actually work, you need for this change of variables to be an invertible function. And if you double count, it's not invertible, so it just doesn't work. You're 2 to 1 instead of 1 to 1. Okay. The rest of this example is details that we've already gone through that kind of thing. No, I know. Yeah. But it's details of a sort that, so the main reason I have this example, in other words, is so that I can talk about theta going from 0 to 2 pi. Yeah. And if you want to look at the rest of the details, you can. Yeah. Okay. So in general, when you're using polar coordinates, just be aware Almost always, not always, there are some rare, mostly manufactured examples where you would do otherwise, but most of the time, put the differentials in this order. Just tends to work out that way most of the time. So in this class, I would encourage you to pretty much just assume that you're going to be in that order. So just kind of always use dr d theta and never use d theta dr. Okay. Here's another one that I think is a big point, really save you a lot of oopses and trouble and this kind of thing. Write this all at once. Right, r dr d theta all at once. Because here's the thing, every time you do an integral in polar coordinates and thus would need the dr d theta, you will need the stretching factor r also, every time, right? So it just really makes sense to just write it down all at once because you'll never need the one without the other. The very common story that I see a lot is for students to write down dr d theta alone because, hey, man, don't bother me with stretching factors. I'm thinking about bounds right now, right? I'll fill in that stretching factor later. And then they get into the bounds and thinking about the shapes and the slices. And then when that's all over, they, whoops, I forgot. And they forget to put in their R. And it costs a lot of points. And I know that in vast majority, I mean, in some cases, I'll say, a student who didn't put in the R just forgot. But in other cases, the student didn't know that there was a stretching factor to be put in, right? And I can't grade on my speculation of what I think someone might have known based on zero evidence on the page. I just can't grade that way, right? So it costs a lot because that stretching factor, this factor of R, is a really big deal. It's one of the most sort of substantial aspects of doing an integral in a coordinate system. So it's dangerous, right? It's a dangerous situation, and you want to make sure that you don't accidentally step on this little landmine. And my best solution for how to avoid forgetting it is to always write this down all at once, and I think it'll help a lot. So just got to kind of train yourself. Always, you know, r dr d theta is a thing that you write down. That's what you write down when you're doing polar coordinates, so that you don't forget. Okay. And just like with every other kind of integral that we've talked about, if you want to find the bounds, identify the points that correspond to those bounds. Identify what curves or surfaces, depending on the context. Identify what geometric, item they are part of, and then find the equations of those items, and then you solve those equations to find the bounds. Okay. All right. So another example. We just have several examples to go through here. What if our region R, our domain for our integral is this thing we call an annulus? It's like a ring. I like to think of it as a moat around a castle, that kind of thing. So there's our domain. Right? So how do we compute this integral? In particular, I'm going to do the integral of 1 over the square root of x squared plus y squared. So now a lot of people would approach this by saying, oh, well, look, this is a weird shape, but it's a sort of combination of two simpler shapes. I'm going to think of this as being, let's see here, it's like this. It's the big disk. I'll compute that integral first, and then I will next compute the integral on the small disk. Right, and if I take the integral on the big disk and subtract the integral on the small disk, then what will be left over, one would think, would be the integral on the domain I'm actually interested in. And this is there's a certain amount of cleverness in that approach, and that's all well and good, except it doesn't work in this case because neither one of these integrals here is defined. Because for those domains, right? Those domains include the origin, and at the origin, the integrand blows up, right? And so, one could say, oh gosh, well, we can, let's define a whole new concept of an improper integral, right? And we can compute these as improper integrals, we might speculate, right? But that's a long way to go, and it's harder than it sounds, and it is not something that we're going to do in this class. So this approach just doesn't work, is the punchline. Okay, so here's another thing you might do. You might say, okay, well, I'm going to do this in rectangular coordinates. I'm going to do so by slicing it into 4 pieces. I can use that piece and this piece and this piece and this piece. Okay, 4 separate integrals. The problem is that's 4 integrals, right? And furthermore, I mean, there is the little matter of the fact that doing it this way, having these 4 separate regions, our bounds are going to come from circles, in particular the rectangular equations of circles, in which I will have to solve for one of the variables. I'm going to have square roots. So these are 4 hard integrals. So let's call that plan B, right? That's hopefully we won't have to do that. So the much easier solution is do it in polar coordinates. It's very easy in polar coordinates. No problem at all. Theta goes all the way around 0 to 2 pi, right? Then you say, okay, well, I'm going to fix a value of theta for a given value of theta. Let's arbitrarily say something like that. For that value of theta, here's what my theta slice looks like. On that value of theta, what's the range of values of r? Well, r starts at that point, which is on that curve, which has this easy polar equation. I'm looking for r bounds. So I solve for r in this equation. That was easy. And boom, 1. And then likewise, to find the upper bound for r, what is that upper bound? Well, it's based on that point, which is on that curve, which has that equation. Solving still for r, so conveniently already solved for r. And there's my upper bound. So nothing to it in polar coordinates. Now do notice, I'm going to draw your attention, r d theta, right? Don't forget, gotta make sure to put that r in there. And if you write this down all at once, you won't forget. Right? And conveniently, I should come back up here like this. The integrand simplifies to 1 over r, and that just makes good news happen in the eventual algebra. Now my new integrand is just 1, world's easiest antiderivative, and easy details, answers 2 pi. Everybody good? All righty. Here's another one. So our region that we're interested in is going to be part of this disk, but specifically it's the part of that disk that is not including, that's what that little backslash means. That means not including the points that are in this disk. So we're going to remove those points that are in the purple disk, and what that leaves is this shaded region here, this partial eclipse, right? So on that region, how do I proceed? Now there's a particular trick I want to show you in this one. Sometimes geometry is your friend. I suppose one thing you could do, and this would be fine, and it wouldn't even be that bad, but one thing you could do is write down the equations of these circles in polar coordinates. Side note, there's a little bit of work to be done there. In particular, right? Figuring out how to convert this, this sort of, make this an equation, of course, and how to convert that given blue equation into polar coordinates. Well, you got to plug in the coordinate system conversion formulas and blah, blah, blah. And it's not bad, but it's a certain amount of effort there. Something we're going to have to do anyway, though. And you could proceed by saying, well, I want to find, for example, my upper bound for theta. My upper bound for theta is based on that point right there. That point is where both of these equations apply, and then you can solve for theta. And that's fine. It'll get you to the right answer. But do notice that there's a much easier way. Much easier way is to say, notice in the geometry here that this distance here is 1 because, well, it's a radius of that circle, right? I can just see from this given equation over here, the second equation, clearly that radius is 1. Secondly, that is 1. And then thirdly, notice that this is a radius of that circle, and that radius is also 1. And so altogether, what I have here is a equilateral triangle. Equilateral triangles were well understood. And in particular, I know what this angle is then. That angle is negative pi over 3. So my lower bound for theta, negative pi over 3. And then analogously, same picture up here, analogous argument. That means that this angle here is positive pi over 3, upper bound then for theta. Everybody see what happened there? So sometimes you get lucky with the geometry. Always keep your head on a swivel. Always be on the lookout for the possibility that maybe something nice will happen. I mean, circles are great, by the way, right? Of course, I mean, circles, knowing that you're dealing with circles means that you've got there's a bunch of distances that you know. Who knows, one of those might be useful, is a sort of point of view you might take from this. Okay. All right, now let's finish this one out then. So we fix a value of theta. Let's look for that value of theta. Here's the actual theta slice then. And we think about lower bounds and upper bounds. Well, the lower bound for R is going to come, well, it's that point, which is on that curve, which has that equation. By the way, that equation, of course, came from there. I am looking for an R bound, so we solve for R, and of course that gives us 1 effortlessly. Yeah, everybody happy? Okay. Upper bound, how do I find this upper bound? Well, it's this point, which is on that curve, which has that equation. By the way, here's that same sort of like, well, yeah, but there was a certain amount of effort that goes into that one, right? And make sure you can do that. Go back to chapter 1, make sure you remember all the little, it's just plugging in, but nevertheless, make sure that you are efficient with that. This point then satisfies that equation. Reminder, I'm looking for an R bound. So in this equation, I need to solve for R. Good news, it's already done. And that gives me my upper bound. How are we doing? Okay. All right. Notice how useful the picture is, by the way, while I'm cleaning up here. I'm a big fan of having a good picture. Notice how it takes up a significant fraction of the page. A nice big picture is helpful. So otherwise it gets very sort of cramped and crowded, and then you can't see what you're doing on your own figure. That's not good. So give yourself a nice picture to work with. Try to take care in making it reasonably representative and clear. Okay. And notice I wrote down RD theta all at once so that I don't forget my R, which would be it says leaving money on the table, it's just that one, just remember that one thing, that alone is worth points. So make sure not to forget that. Okay, here's a fun one. Now this one's not very geometric, but it's actually a historically significant calculation. I think this is really interesting. Y'all may be aware of these things called normal distributions. If you've ever had a stat class, presumably you know about normal distributions. Very important. And not just because the formula looks nice, right? But there are natural reasons. In some sense, when you take any distribution at all, any random variable at all, and if you repeat it over and over and over again and then average your results, as you keep repeating more and more and continuing to average, then modified appropriately, those averages will have a normal distribution. So this is not an arbitrary distribution. This is a fundamentally important, whether we like it or not, distribution. If you've had a stat class, or if you've had a single variable calculus class, a Calc 2 class here at Duke, then I would imagine you probably also know that the way we compute probabilities from distributions is by taking integrals. So this integral here is just fundamentally important in statistics. It's really important to be able to compute this integral. And that's tragically opposed to the unfortunate reality that finding an antiderivative of this function, antiderivative of e to the negative x squared, is not possible in what we call closed form, namely without using Taylor series or something really annoying like that. So how are we going to compute this integral if we're not just going to find the antiderivative and plug in the bounds? Oh yeah, improper integrals take a limit, blah, blah, right? If we can't do that, what on earth are we going to do? So a famously powerful trick is to give this thing a name. We're going to call it J. We are not going to compute J directly. We're going to compute J squared. So J times J, and here it is, J times J. Now you may object and notice that one of these copies of J is written with a different dummy variable, and I point out, yeah, right, dummy variable, doesn't matter, right? Both of these things say we're interested in a certain function, and we're going to let it range over these same values and multiply by the same width. We're just going to call them by different names as we're doing so. Doesn't make any difference. Okay, first slick move. This is just a number. This is a calculation on its own. It's a value. It's a constant. It's J, right? Constants, you're allowed to pop inside of an integral like so. Okay, now what we have here is kind of an iterated integral, isn't it? The variable further to the outside, y in this case, constant for the purposes of the inside integral. If y is constant, that means e to the negative y squared is constant. And again, constants are allowed to pop inside of the integral. Now this seems very sort of like inside out, twisty turny, weird, but perfectly legal. All right. And so what we have then is this iterated integral. Now keep in mind, this is computing J squared. Okay, the slick move, the really powerful move is to say this, say, oh, look, iterated integrals are double integrals. So what we have here is a double integral where x and y are both ranging over all possible values. So this is a double integral on R2 itself. Double integrals we can compute with polar coordinates. All right, polar coordinates, let's think about what's happening here, theta. All directions of theta, 0 to 2 pi. For any given direction, r goes, all the way out to infinity, so 0 to infinity. Don't forget, dx dy is r dr d theta. Don't forget that r, critical r. And it seems like we're just kind of playing games, taking a question and taking a hard question and making it harder and harder. Can't compute this integral, fine, we'll compute the square of the integral, fine, we'll do that square of that integral, we'll do it in polar coordinates. It seems like we're just digging ourselves deeper into the hole until you notice that this inside integral, because of the stretching factor, we now can do an easy, substitution, let u equals negative r squared. This is now an easy integral. And it's super clever. I wish I thought of this. Very few people would have thought of this on their own. Some very clever person did this hundreds of years ago. Anyway, neat fact. And turns out that j squared is pi. And so the integral that we were interested in the first place, square root of pi. So if you ever wondered where that came from in your stat class, this is where. Okay. All right. Okay, so that's all I'm going to tell you about cylindrical coordinates. Oh, let's see here. I need to. Oh gosh, this thing is annoying. Sorry. Let me do. There we go. Okay. I can do this. Okay, so on to cylindrical coordinates. We've already talked about the stretching factor. We know what the cylindrical stretching factor is, and I'm going to make the observations that just like with polar coordinates, we can do the pullback. You know, that there is a change of variables function, and I can pull the integral back through the change of variables function in the same way. And just like with polar coordinates, the slices that I would do over here in the pullback space, those slices, I can see them perfectly well in XYZ world. So why would I draw, stylus, why would I draw a whole new picture, a whole new world, when I don't need to? Everything I need to see over there, I can see over here. Let's just work off of this picture, right? So very convenient to do so. And with that in mind, this is what theta slices look like, and this is what r slices look like. Highly believable. Okay. When you're doing integrals and cylindrical coordinates, couple of tips. By the way, this bit of my notes, I discovered a typo this morning as I was getting ready for lecture. I don't know how I managed to do this, but in my initial draft of these, I had these two differentials reversed. That doesn't make any sense. I don't know, it's a mental, brain spasm, whatever, typo, who knows what happened there in my head. But anyway, I've corrected it now, and these are now in the correct order. I meant to write this as dr and d theta, as you see here. The updated, now uploaded copy, corrected copy of the notes went in like 10 minutes before class. So if you haven't already done so, within minutes before class started, you want to download the new copy or scratch out, fix it, and make sure you have this there and not have it. Reversed doesn't make any sense. Okay. All right. Good news again. You have 6 different orders to slice, but you'll almost always use one or the other of these two. The way you remember these is that the r and the theta should stay together and in that order. And so the only question is, do you put the dz on the outside or do you put the dz on the inside? Pretty much other than that, I mean, the dr and the d theta should be together, and they should be with the dr inside of the d theta. And so just pick between these two. And very often, both of them will work fine. But sometimes z will be given as a function that's naturally thought of as a function of r and theta, in which case, if z is a function of r and theta, you're going to want to do this one. On the other hand, sometimes r and or theta will be more naturally viewed as functions of z, in which case, do that one. Okay. All right. Again, don't forget your stretching factor. Again, if you write the stretching factor in at the same time that you write your differentials in, it'll make it harder to forget. And again, it's an unavoidably big deal. If you forget your stretching factor, there's nothing on the page to indicate that you knew it should be there. And it has to, we really need it to be there. So view this as easy money. View this as easy points. All you got to do is remember that stretching factor and you get points. This is a good thing, right? But that said, you do have to remember. Okay. And then again, bounds come from looking at certain points. Those points are going to be on certain geometric objects. Those objects have equations. Solve the equations to find the bounds. Old news there. So let's see an example. Here's the upper half ball, the upper half of the unit ball. So this solid there. We're going to do our slicing, cylindrical slicing. We're going to use slices like this. Right, so this is what theta slices look like, for example. And so let's start with this ordering of the differentials, d theta on the outside. Arbitrarily, we're going to do the other one next, by the way, but we'll get to that in a minute. Starting with d theta on the outside, what's my range of values of theta? Well, it goes all the way around. So 0 to 2 pi. Is everybody good with that? All righty, then we fix a value of theta. Let's say we fix this value of theta here. What is that theta cross section of our solid? Well, let's see here. I'm gonna, oh gosh, I guess I better stick with orange. Our cross section is this sort of shaded thing here. All right, there's our theta slice. On that theta slice, we now want to ask what's the range of values of R. So where does R start? Where does R end? Well, R slices look like that. Right, this is what happens when you fix a value of R on that fixed value of theta. Now you got to just think that through geometrically. Right, you might say, that's what happens when you take these kinds of R slices of these kinds of theta slices, right? Of, one of those kinds of theta slices. And so with that in mind, oh man, okay, fine. There we go. First slice is going to be there. Last slice is going to be there. Now you can play the usual game, identify what surfaces these are on, do some algebra, or you can observe that, well, the first one's obviously the origin. That's where R is obviously 0, which is fine, right? And then you can say, well, the second one is obviously at the edge. That's clearly a radius of my ball, which is given to be A. So, yes?
Why would we not instead integrate from 0 to that curve equation? Because if we do
0 to what?
Slices with different z values, it would be smaller than that.
Well, because we haven't gotten to z yet. So remember the process. Now, what you're describing is kind of along the lines of what we'll be doing here. But so you look at fixed values of z when z is further to the outside, right? But critically, z is on the inside here. And let's see here. Yeah, so yeah, if z was on the outside, then yes. And we will do that. Okay. Yeah. So here we've got dz on the inside, so we'll deal with z when we get there. Yeah. Okay. All right, so R bounds. Good. Now we fix R. Here's an arbitrary R on our fixed theta. And now let's think about z slices. So, here's the start. And again, sometimes the fish jump in the boat. Z is clearly 0 there, so boom. Right. And then let's see here, our ending value of z is going to come from that point. And here we're going to go ahead and actually do the work, the sort of the algebraic work. That point is on what surface? What do I know about that point? Well, it's on the sphere, which has that equation. Notice I've got this already in cylindrical coordinates. We're doing a cylindrical integral. We're going to need cylindrical coordinates. So that's the cylindrical equation of the sphere. I am looking for z bounds. And so in this equation, I will solve for z. And solving for z gives me my upper z bound. Everybody happy? Yep.
So when you're like in problems like this, on like an exam or something, are we going to be told what coordinates to use?
Not necessarily. No. Yeah. I mean, so diagnosing and making good choices is part of it. So, you know, I mean, it's a great question. I think you want to think in terms of what coordinate system makes the objects in play look good. And so now this being a sphere, you know, you could think spherical coordinates. Of course, we haven't talked about spherical coordinates yet, right? So our choices on this three-dimensional solid are rectangular or cylindrical at this stage. And cylindrical equation's a little bit nicer, one could argue. There's a little bit of square roots there, but not much. Yeah, so this is probably better than rectangular. But yeah, you're quite right. There is a, you know, pick your tool. And this is a tool for your toolbox, and you gotta, you know, try to, you know, eye up the circumstance and pick the best tool for the circumstance. Yeah. Yep. Now that said, sometimes I will give explicit instructions, but I will only, that's the kind of thing that I'll do if I think the question's like too hard otherwise, and I want to, you know, I want to make the problem the appropriate level of challenge by, I'm going to start you, you know, a third of the way there. But yeah. Right. Okay, so let's do the other way now. Our other reasonable option, DZ on the outside instead of the inside. Here's what Z slices look like. A Z slice of this disc, excuse me, a Z slice of this ball is a disc. Starts there, ends there. That's the origin where Z is clearly 0. This is a radius where Z is clearly A. Everybody good on the Z slicing? Okay. All right, so Z, 0 to A. Now we're going to fix a value of Z, such as what I have highlighted there. Now we're going to think about theta. What's the range of values of theta? Well, theta goes all the way around, 0 to 2 pi. Specifically, I emphasize, it's the Z slice that we're looking at there that goes all the way. I mean, the solid itself does too, but that's not the point. The point is the Z slice also goes all the way around. Okay, then we fix a value of theta in addition to our value of Z, and our theta slice of our Z slice now looks like that. What's the range of values for R? Well, R starts there, which is on the Z axis, where R is clearly 0. No problem. No justification necessary when it's that obvious. That's perfectly clear. Yeah, last value, this one is not obvious. The upper bound for R comes from that point. That point is again on my sphere with that equation. Now reminder, it's easy to mess this up. This is where there's a sort of a bump in the road. Make sure to remember what you're solving for. Here we're looking for the R bound in terms of theta and Z. So in this equation, we want to solve for R now, not Z, to get my upper bound for R. Everybody happy? Okay. Okie dokie. I'm pretty sure y'all have started to notice a pattern here. So what does slice look like if we're using spherical coordinates, right? I mean, the setup is all the same, pullback and all that. So what do, for example, theta slices look like? Well, we already know what theta slices look like. What do phi slices look like? What happens when you fix a value of phi? You know, looking in the XYZ world, if phi is a fixed constant, what do you get? And well, you get one of these kind of, well, you get a cone, right? Now, it's just a geometric appeal, but that's what happens when you fix a value of phi. And what happens when I fix a value of rho? There's a rho slice. A fixed value of rho, of course, is going to be kind of a part of a sphere. All right, so these are your tools here, and we're going to slice up with these tools. Again, there's good news. You're almost always, even more almost always than the other cases, almost always going to use this order right here, d rho, d phi, d theta. And it's not that you can't use the other orders, it's that this will almost always be at least as convenient and desirable. And it will usually be much more convenient and desirable than your other 5 options, right? So for the purposes of this class, I would consider this to be, this is just what you do. Don't even really spend any time thinking about other possible orders, just always use this order. Okay. By the way, you can kind of see one of the reasons why these slices here are spherical slices. That's geometrically really hard to think in terms of. If you were to take a spherical slice of some solid, oh my God, it'd be super hard to draw if nothing else. Likewise, conical slices would be brutal. All right. Theta slices, not that bad. Yeah. So that's a geometric motivation for why we put theta on the outside, and et cetera. You can think through, what would happen if I took, d rho slices of a d theta slice, and I think you'll find that it's curved, and that's undesirable. But putting d phi next gives you nice straight slices. We're going to see this play out. Okay, again, always write down the stretching factor simultaneously at the exact same time as you write down these differentials. Write down this as a single thing at a single time. Rho squared sine phi d rho d phi d theta. Just think of that as a single, you'll memorize that little grouping and just write it down all at once so that you don't forget. Same reasons as the others. And again, we know our slicing process. You find points, identify surfaces, etc. Okay, so let's get our hands dirty. Suppose you have a ball, radius A, centered up on the z-axis so that it's kind of sitting on top of the origin there. How would I slice this up? So starting with theta slices. Theta goes all the way around. Geometric appeal, right? We can see from the picture. Everybody good? Okay, now we're going to focus our attention on the theta slice. Here's the thing, that theta slice that we're looking at, it's at some kind of an angle, and it's not that we can't work off of that picture, but sometimes life is a little easier if you just redraw the picture. This is still that same theta slice. I'm just drawing it so that I'm looking straight at it. I don't know, I find this very often makes the geometry easier to think about. Right? So this theta slice, what I've got here, looks kind of like that over in that world, but from my geometric intuition for what the geometry actually is, I know that that's a half a disk, and I can come over here and sort of do a better job at drawing a half a disk, looking at it straight on. And it's easier to see the geometry of this half disk looking at it straight on than it is to see, looking at it, kind of from an angle and from an altitude, right? I mean, that's a weird sort of perspective to have on it. So you don't have to do this, but I think you'll find it very helpful. So here's my theta slice. Let's talk about the range of values of phi. Now, a lot of students will get this wrong. A lot of students will look at this and say, oh, well, 0 to pi, because, it's a half a disk, it goes halfway around a circle. Isn't that 0 to pi? This is all wrong. Because, keep in mind, we're talking about phi, and phi is measured from the origin. It's not measured from the center of whatever you might happen to be looking at, right? It's very strictly measured from the origin. So phi slices actually kind of go like this. And your very last one is going to be at pi over 2 after your very first one, of course, being at 0. So 0 to pi over 2. Everybody see that? Now, there's a lot of sort of geometric sort of just got to see the picture going on here. Okay. All right. Okay, now then finally, fixing a value of phi. Right, here's our phi slice. Let's talk about rho then. Rho starts there. That's clearly 0 because it's the origin where rho is obviously 0. No problem there. This point here, you do have to kind of backtrack and remind yourself where all this came from. That point, where that came from, it's really a point on this theta cross section up here. And from this picture, a little bit more clear to see, that's a point on the sphere. So how do we write down the equation of the sphere? Well, there's some work to be done there, right? I mean, this sphere, you can write down the equation in rectangular coordinates because you know the center, you know the radius, write that down in rectangular coordinates. Having written it in rectangular coordinates, you can then convert to spherical coordinates. And again, make sure that you can do that, right? Make sure that you're proficient, you know, at writing down the equation of that sphere. And this is what it ends up being. Okay. And solve for rho, of course, whoops. Yeah, so in here, we solve for rho. And there's our upper rho bound. And we're in business. Reminder, of course, rho squared sine phi d rho d phi d theta. All that's important. Make sure not to forget that. And so my new integrand, therefore, is this business right here. Yes?
Sorry, can you explain again how you got the formula for what's called rho?
Oh, yeah, sure. So, so it comes ultimately from the equation of this sphere, right? And this sphere I can write down in rectangular coordinates because I know the center and I know the radius. So this is x squared plus y squared plus z minus a squared equals a squared, right? And that comes from knowing where the center is and what the radius is. And having it in rectangular, then you convert just like we did in chapter 1, just plug in the coordinate functions. Yeah, okay. Okay, I've already said this, I'm gonna say it again. And you're probably noticing, and you're gonna notice even more in the next couple of examples, good picture is a big deal. It's really important. If you're not good at drawing pictures, get good at drawing pictures. Now, there are things to know, right? There's techniques to know about how to draw. I've pitched it before. I'm going to pitch it again. I have some videos on my YouTube channel, miscellaneous topics playlist, drawing 1 and drawing 2. It's an hour's worth of discussion of me telling you everything I know about how to draw mathematical figures and then going through detailed discussions of hard examples. And I think you'll find it helpful. Yes.
Were you able to find is it possible to find the equation for rho without plugging it in?
Without starting in rectangular coordinates?
Yeah, like without just.
That'd be tricky.
Could you see it? Are you able to do that?
Maybe. I think it'd be hard.
Yeah.
I don't want to say no, but I'm gonna. I don't think it's. I mean, I could probably get clever about it, but I don't think it's a good road to go down, right? And I think it's good to have have a nice algorithm that's consistent that will always, air quotes, always work. Yeah, right. Okay, so yeah, so make sure to learn technique, and then by the way, keep in mind, I mean, this it requires practice. Drawing is a skill. It's a physical skill, and so it unavoidably takes practice. It'd be nice if we could just kind of upload the skills and just automatically be able to do it like in the Matrix, but this is not how it works. So give yourself the time to practice and get better at it. Okay. Here's another example, another sphere, another offset sphere, given radius, offset this time over on the y axis. And you just kind of got to go through and play the game. So here's what our theta slices look like. And the first one is over there. And then it goes over to over there. That's because it's offset, right? So this sphere, this ball does not kind of surround the z-axis. It just sideswipes the z-axis. So you don't get 0 to 2 pi. It's just 0 to pi. And one thing you might do if you want to, make it a little easier to see that from a picture would be to draw this picture as seen from directly above. Right? If you were to think about, if you were way up, and looking straight down on it, then you can, see a little better maybe. Okay, then we fix a theta slice. We look only at that theta slice. Now I claim that the theta slice of this ball is a disk. I claim, right? Geometric appeal. So that disk, now again, I can think about this thing as being, living inside of this plane that I'm looking at from a weird angle. I like to redraw so that it's easier to see what's going on. So I'm going to look at this picture to the right instead of the one to the left because it's easier. And having redrawn it, I can now ask, okay, well, what's my phi slicing? Well, my phi slices are kind of like this. And in particular, the first one is going to be up there at 0. And then the last one is going to be down here at pi. So phi goes from 0 to pi. Cool. Let me see what we're doing on time here. Oh my gosh, I'm almost out of time. Okay, fine. Now we fix a value of phi. There's what our phi slice looks like. Rho clearly starts at 0. Gotta love it when that happens. And rho ends at that point, which you can really think of as being that point, which of course is on the sphere that you have information about. You can then derive that equation. Again, there's algebra to be done in there. Make sure that you can do that algebra. And we're looking for a rho bound. And so we solve for rho, and that becomes our upper bound there. Okay. All right. So almost done. There's one more example I want to do before I can claim we're done with the coordinate system integrals. Anyway, it is what it is. Time's up. Good to see y'all again. Thanks for coming, by the way, on the day before spring break. Good for you. And see you after spring break. I hope y'all will have a great spring break. See you later. Oh, and of course, as usual, if you came in after, I check attendance. Make sure I mark you off.
I came in after.
Yeah. Okay. Yeah. Give me just a second.